Okay, so this is a video in which I will read a scientific paper. I've been wanting to do a series in which I just read scientific papers and do my best to understand them. I'm going to start on a topic that I don't know much about, the search for exoplanets. The reason why I'm doing this is because I want to get a better grasp of the reasoning that's happening in scientific papers. I'm interested in the step from having a data set or collecting data to interpretations of the data, conclusions, and I want to see how that is done in scientific papers. I have a theoretical understanding of it and how it should be done. I want to see how it's done in practice. So the paper that we're going to start with is called A Search for Substellar Companions to Solar Type Stars. Apparently it is a important paper or an influential paper within this field. It was released in 1988, and the first author is Bruce Campbell. And yeah, I don't know much about it, so let's see. I did read a little beforehand. I read the abstract, and well, we can read through the abstract, although I didn't think it gave me that much, but let's read it through just for the sake of it. So, relative radial velocities with a mean external error of 13 meters per second, root mean squared, have been obtained for 12 late type dwarfs and 4 subgiants over the past 6 years. 2 stars, I don't know how you say that, Ori A and SEP show large, within parentheses, a few thousand meter per seconds, velocity variations, probably due to stellar companions. In contrast, the remaining 14 stars are virtually constant in velocity, showing no changes larger than 50 meters per second. No obvious variations due to effects of other than center of mass motion, including changes correlated with chromospheric activity, are observed. 7 stars show small but statistically significant long-term trends in the relative velocities. These cannot be due to 10 to 80 Jupiter mass brown dwarfs in orbits with a period less than 50 years, since these would have been previously detected by conventional astrometry. Companions of 1 to 9 Jupiter masses are inferred, since relatively massive brown dwarfs are rare or non-existent. At least as companions to normal stars, these low-mass objects could represent the tip of the planetary mass spectrum. Observations are continuing to confirm these variations and to determine periods. Okay, so this is the basic reasoning they have behind the claim that there might be some planets. That's how I interpret it. Okay, so there's different parts to this abstract, but I'll take one thing at a time. They're saying here that there's 16 types of stars that they've observed variations in the radial velocity, and for 2 of these, this is probably due to stellar companions, and that might be planets. But the remaining 14 stars are virtually constant in velocity. Then they go on to say 7 stars. I don't know if this is additional stars. Maybe they're making a distinction between late type dwarfs and subgiants. I thought that would still be considered stars. I guess we'll learn more as this moves on. Anyways, they mention that these also have long-term trends in relative velocities, and they can know that these are not due to substellar companions of 10 to 80 Jupiter massed objects, because these would have then already been detected by conventional astrometry. However, companions of 1 to 9 Jupiter masses are then inferred. And as massive brown dwarfs are very, very rare, at least as the companions to normal stars, these low mass objects that they believe they can see in these relative radial velocities could be planets, or as they put it, could represent the tip of the planetary mass spectrum. And there's continuing observations that confirm this. So it's pretty interesting. I don't know what the state of the field was in '88. I don't know what the state of the field is right now, but the way that I interpret this is that, you know, they're kind of discovering what the exoplanets for the first time talking about these the type of data that could mean that there's planets around these stars that they've been observing. So pretty interesting stuff. Okay, so if we continue reading the introduction, I have a little part here which I can't really understand the significance of, but let's read it anyways. The nature and existence of objects less massive than the limit of the hydrogen burning main sequence, around 0.08 sun masses, are important for a number of current astrophysical problems, including A, determination of the minimum Jeans mass, B, the mass limit for core hydrogen burning, C, the cooling sequence for brown dwarfs, D, identification of the missing mass component of the galactic disk, and E, the presence of massive halos around galaxies in general. At the extreme low end of the substellar mass spectrum are planets, which are distinct from brown dwarfs in that they probably form by solid particle accretion in dissipated circumstellar disks rather than by fragmentation and gravitational collapse of interstellar gas clouds. Detection of planetary companions to stars would answer a long-standing question in astronomy on the ubiquity of planetary systems, as well as help in understanding the formation processes of stars and planets. Okay, so I don't know why they mentioned this. I don't see how that relates to the existence of planets, but that's probably due to my lack of knowledge. But anyways, it's pretty straightforward, the rest. So we can go on. The detection of substellar mass objects provides, however, a serious technological challenge. The low mass and luminosity of these objects make the task of detecting them, let alone learning their physical characteristics, formidable. The most difficult problem is to detect extrasolar planets, and techniques for identifying objects of Jupiter mass 0.001 mass of the Sun or smaller have been reviewed by Bracewell and McPhee and Black. These techniques fall into the broad areas of direct detection by imaging or radar and indirect detection by high precision astrometry, radial velocities, or photometry. In all cases, the expected signals are close to or below the limit of current detection capabilities. Okay, so they're talking about some of the difficulties in detection of substellar mass objects. And then that the most difficult problem is to detect extrasolar planets. Okay, so I guess there's other type of substellar mass objects than extrasolar planets. I mean, of course there is, but yeah, okay. So we have developed a radial velocity technique which has sufficient precision to detect the reflex motion of stars due to orbiting substellar or planetary mass objects. We have used this technique to monitor the relative velocities of 23 stars for the past 6 years. In this paper, we will report on the results obtained to 1987 March for 16 of these stars. The precision of the relative velocities and the time span of the observations are not sufficient that we can make a preliminary assessment of the incidence of substellar mass companions to solar type stars. Okay, so here they're talking about 16 stars, and here they are talking about 7, so that's 23. So I guess now we have an explanation for this. And so they've been working on this for 6 years. And okay, now they can make a preliminary assessment, so that's pretty interesting. And now we will get into the observational procedures, so I guess how they made these observations. Okay, so part 2, which is called the hydrogen fluoride absorption cell technique. So this is part of the observational procedures, so kind of the methodology. This technique was first described by Campbell and Walker. The principal feature of the technique is the introduction of an absorption cell containing hydrogen fluoride gas ahead of the slit of a Coody spectrograph. Okay. Absorption lines of hydrogen fluoride are superposed on starlight passing through the cell as shown in figure 1. This is figure 1. The hydrogen fluoride lines provide a wavelength calibration which is insensitive to optical and mechanical effects within the spectrograph. This is in contrast to the conventional technique in which separate beam of photons from a comparison source provides wavelength calibration. Instabilities and non-uniformities in the spectrograph components can lead to relative displacement of the stellar and comparison spectra in the wavelength direction, which can result in relatively large systemic errors in radial velocities. Hydrogen fluoride was chosen for this application on the advice of Hertzberg. The R branch on the 3-0 vibration rotation band of the hydrogen fluoride is nearly ideal because A, it produces strong absorption lines for a cell length of only 90 centimeters. The lines are well spaced in wavelength so that many stellar lines fall between. And C, there's no interference by lines of rare isotopes of hydrogen fluoride or by telluric absorption lines. To be sure, hydrogen fluoride is a noxious gas, and so care in handling is required. Stars were selection for observation if they were yours. Okay, so here they're gonna start talking about the selection of stars for these. What do they call it? Observational procedures. I have no clue what they are talking about. So it's some sort of calibration technique, but I'm not entirely sure how a spectrograph works. I don't know what this cell length is, so I'm gonna look that up quickly and yeah. Okay, so I had to read up a little on this, what the point of this gas was, and I realized just how little I know about this subject. Of course, what we want to know here is the radial velocity of these stars, and the question is, how do we know that? And we do it in part, or at least we can be informed by the Doppler effect. So one can imagine if the star moves away from us, if it's moving away from us to a certain velocity, the frequency of the light that hits us is going to be lower than if it was moving towards us. So if the frequency is lower, the wavelength is going to be longer. So that's how the Doppler effect can inform us about the velocity of the stars. And if we put a cell of hydrogen fluoride gas ahead of the spectrograph, so the spectrograph is an instrument that breaks down the light into components of wavelength like this. If we put a cell of this gas in before, so that the light travels through this before it hits the spectrograph, then that can act as a reference grid of sorts, apparently. I don't understand it in much detail more than this is a way of calibrating the measurements. Okay, so we can move on. Stars were selected for observation if they were dwarfs or subgiants, were not known to be spectroscopic binaries, and had delta more than minus 40 degrees. A brightness limit of I less than or equals to 4 was imposed to ensure exposure time less than roughly 1 hour. Rapid rotators and stars earlier than type F5 were excluded, since such stars have too weak spectral lines for velocities of the highest precision. Okay, furthermore, they're taking into account the accuracy of the measurements. We've been accumulating spectra of these stars since late 1980 with the F82 Curie spectrograph and the hydrogen fluoride cell of the Canada, France, Hawaii 3.6 meter telescope. Okay. The detector is a Redicon photodiode array with 1,872 elements, which is photon noise limited for the typical signal to noise ratio attained about 1,000. In such high quality spectra, the positions of strong absorption lines can be determined to about 0.01 pixels or 0.15 micrometers, which in the absence of systematic errors result in a velocity precision of about 10 meters per second for the ensemble of lines observed. Oh, right. So they're talking about the tools they're using to make these measurements. Changes in the wavelengths of the hydrogen fluoro lines can occur with variations in temperature and pressure in the absorption cell. The slight run-to-run variations in these quantities, delta T of less than 4 degrees, delta pressure less than 2 torr, are adequately measured from the strengths of the hydrogen fluoride lines themselves, and corrections are made for wavelength shifts using the calibrations of Campbell and Walker and Campbell. So referencing other papers. This procedure avoids depending on temperature and pressure meters, which could drift in gain of 0 point on a timescale of years. For each stellar spectrum, the mean exposure time, which can differ significantly from the mid-exposure time, is derived by integrating the output of the spectrograph flux meter. This step is essential in deriving accurate velocity corrections in the solar system barycenter, because the acceleration of the telescope by Earth rotation alone is about 2 meters per second per minute. Following each stellar exposure, flat field spectra are obtained with special illumination systems designed to precisely mimic the shape and co-illumination of the beam of starlight from the telescope. Experience has shown that such care is essential for accurate flat fielding. Okay, so basically they were once again talking about how to get accurate measurements. Part B here is the reduction to relative velocities. And they write, we give here only a brief summary of the reduction procedure as the details have been described by Campbell et al. The reduction of these data was greatly facilitated by the spectrophotometric reduction package already sent. Each stellar spectrum with hydrogen fluoride is first normalized relative to a reference stellar spectrum obtained without HF lines and to a reference HF spectrum obtained with a flat field lamp. This ensures that all instrumental effects are removed consistently from each stellar HF spectrum. Line positions are then estimated after alternately cancelling either the stellar or HF lines by spectral division. Positions relative to those in the two reference spectra are derived using the difference technique of Feynman and Gillespie. Note that relative positions of primary importance are of primary importance since we're only looking for velocity changes. Yeah, okay. Well, that makes sense. Approximate absolute line positions are only needed for registration of the spectra prior to spectral division. The relative line positions so determined require correction for two subtle effects. The first arises from convolution of the instrumental profile on blends of HF and stellar lines and has been discussed by Campbell and Walker. Although this effect can introduce a slight random error in the velocities for individual stellar lines, it's not a problem in practice because severe blends are rejected, while adequate corrections can be derived for weaker blends. Okay, I'm not entirely sure what they mean by blend here, if it's just a blend of how much HF you have. But let's move on. The second effect discussed by Campbell is more serious since it can introduce a systematic error in the velocity from each spectrum. Changes in the asymmetry of the spectrograph instrumental profile can cause apparent displacement of spectral lines which are a function of line width. This is important since the hydrogen fluoride lines are on average about twice as wide as typical stellar lines. We correct this by measuring the instrumental asymmetry from HF lines and by modeling the effect of the asymmetry variations on each line of each spectrum. Relative velocities are determined from the corrected line positions by an iterative procedure in which the HF line positions provide the 0 point, while both the HF and the stellar lines provide the higher order terms of the dispersion relation. Weighted average velocities are then determined from typically 10 to 12 lines in each spectrum. The line weights are derived iteratively from the scatter of each line relative to the mean velocities in all spectra. This varying degree of scatter from line to line is partly an effect of line strength. I don't know what they mean by line strength, but is probably also related to run-to-run changes in the high-frequency components of the dispersion relation. See Campbell et al. 1981. Finally, the mean velocity of each spectrum is corrected to the solar system barycenter using routines of Stumpf. Okay, so they are once again describing in more detail how they get these measurements. Table 1 summarizes the results for 16 program stars up to 1987 March. The first 3 columns show the times of observation, barycentric Julian date, the signal to noise ratios of the spectra per continuum pixel, and the apparent relative velocities. The 4th column gives the relative velocities after correcting for the run-to-run 0 point variations in the velocities. This is accomplished by using for any given star the velocities of all other stars except these things that I don't know how to pronounce, Aurier and Gamma Sap, observed in the same run to form a correction. In this step, we make use of the fact that none of the program stars appears to show any significant short-term velocity variation, and so deviations about long-term trends can be used to determine the 0 point corrections. Observations with absolute velocity over sigma I more than 3, see below, were not included in the corrections, and no corrections was attempted if fewer than 4 independent observations were available. To illustrate their typical size, we show in table 2 other corrections and their standard errors from all 14 stars for each of the 27 observing runs. Observing runs were always 3 or fewer nights. The 5th column of table 1 shows the net internal errors for the corrected velocities. These internal errors are the quadrature sums of the standard errors from the velocities of all lines in each spectrum, and the standard errors in the run-to-run 0 point corrections. The corrected velocities with one standard internal error bars are shown for each star in figure 2. Okay, so here we have the data. Alright, table 1, relative radial velocities. BJD, what the hell, what was that? Signal to noise, relative velocity, apparent corrected internal error, and what was that? Ohmström. AHR, this is a star then, maybe? And then they just give us the data. Wow. Okay, cool. Alright, part 3, analysis of the relative velocities. Part A, test for velocity variations. Before testing for possible long-term trends in the velocities, we first examine the velocities to check their error distribution. Figure 3 shows a histogram of the velocities divided by the internal errors for the 14 stars without large velocity variations. Okay, let's see if we can find figure 3. Here's the data. Here's more data. Here's more data. Table 3. What's this? figure 2. Alright, this just keeps going. Figure 2. Figure 2. Figure 3. Histogram of velocities divided by internal errors for all stars except Xi1, Ori-A, and Gamma Sep. The curves show the distribution from the simulated velocity data with no trend imposed, so this is solid, and with the slope of 4 meters per second per year imposed, and that's the dashed. I didn't know we simulated the velocity, so obviously I'm not following along. I had to read up on what that was about. Okay, here's a percentage. Alright. Okay, so going back to the text here's where they first mentioned the simulations. So the curves in figure 3 are from simulations of velocity data which mimic the actual data in the distribution of internal and external errors. See below. These curves show the anticipated distributions if no velocity trends are present, and if there is an average trend of 4 meters per second per year. The later distribution matches reasonably well the actual data except for 7 velocities from a total of 371 beyond 3.5 sigma. We ignore these velocities in the subsequent analysis since these discrepant points could otherwise introduce spurious trends. Okay, the remaining data for each star were fitted both with a straight line and with a parabola using a weighted least squares procedure. Weights proportional to sigma I to the power of -2 were used. We have thus determined the first derivative, the slope, and second derivative, curvature of the velocities, and the formal 1 sigma uncertainties in each of these quantities. So the standard deviation. Note that the slope and curvature are derived from independent fits to the data. Yeah, I don't know how you would do it otherwise. The slopes were corrected for secular acceleration. Campbell and Walker, 1985. Secular acceleration. Okay, I don't know what they mean by secular here. And in 2 cases, for the predicted acceleration due to visual binary companions. Okay, so it's corrected for the predicted acceleration due to a visual. Okay, so if it was another star in the system. Compare notes to Shibu A and 61 Sig A below. Values of the corrected slopes S and curvatures C are given in table 3. Okay, let's carry on. The ratios of the absolute values of the slope and curvature to their respective errors, S over sigma S and C over sigma C, are measures of the significance of long-term velocity variations. Figure 4 is a histogram of the observed S over sigma S and C over sigma C. 28 values in total from the 14 stars. Wait, figure 4 is okay. The continuous line in figure 4 is the distribution derived from Monte Carlo simulations of 2,000 sets of velocity data. Each such data set consisted of 27 velocities, the average number of observations per star, okay, with the same time placement as the actual observing runs, while the root mean square deviation of the velocities at each point was just the actual scatter and the velocities for all stars observed in each of the 27 observing runs. Thus, the simulated data accurately mimic that for real stars on average, except that no velocity trends were imposed. Even though the RMS deviations and velocity external errors are not the same from run to run, the simulated distributions of S over sigma S and C over sigma C are the same in our normal distributions with sigma equals to 1. Okay, so I'm not following along, but I'm guessing what they're doing is they're making a simulation of how the velocity would behave if there weren't any planets. So you have something to compare to. So that's what the no observed velocity trends. So they would have no velocity trends. Maybe that's what they're doing. Okay, the observed distribution in figure 4 when compared to that from simulations, so show an excess above about 2.5 standard deviations for 7 stars. S over sigma S or C over sigma C is greater than 2.5, whereas from the simulated distribution we could predict only 0.6 of 28 cases should be above this significance level if no trends are present. We therefore believe that 6 of these 7 stars have statistically significant variations in velocity. Since gamma squared del has the lowest significance of this group, 2.6 sigma, we conclude somewhat arbitrarily that its velocity variation is not significant. I think they mean that it's arbitrarily because this cutoff at 2.5 is pretty arbitrary. On the other hand, the variation for sigma Airy is significant at the of course not significant, damn it. On the other hand, variation for epsilon Airy is significant at the 4.1 sigma level, and so we classify this as a probable variable. For the other 5 stars in the 2.5 to 4 range, sigma 36 UMA A, beta ver 61 ver Shibu A, and beta Akl A. The variations are small but statistically significant, and so we classify these as possible variables. The remaining 8 stars we consider to be non-variable within the errors of the present data set. To test the effect of the leading velocities with velocity over sigma I more than 3.5, we applied a 3.0 rejection criterion and repeated the analysis of the slopes and curvatures. An additional 8 velocities were deleted in this case, but we found that removing these does not significantly alter our conclusions concerning velocity variations. Only gamma squared del drops below the 2.5 sigma significance level. The mean internal error for each star is listed in, okay, we're gonna have to scroll a little. The mean internal error is listed in column 6 of table 3. The external errors sigma E in column 7 are the weighted RMS variations of the velocities for the non-variables, or the RMS deviations about the first or second order trends for the possible or probable variables. The average external error for 14 stars, including gamma SAP see below, is 13 meters per second versus the average internal error of 10 meters per second. The general agreement between the external and internal errors for all 14 stars implies that there is no obvious short-term velocity variations present in any of them. However, rapid variations could be present. A search for these will be the subject of a future publication. For the moment, we note that these must have small amplitudes, since the mean value of some sort of error term is 8 meters per second. Two stars in the present example show large velocity lots of data. What even velocity equal with? Okay. Variations Xi1 Ori A and gamma sep. The star Xi1 Ori A is varying under the influence of a stellar companion. Okay. I've already forgotten what the first part of this sentence was, but alright. So it's varying under the influence of a stellar companion, and is discussed further below. Star gamma set was not previously suspected as a binary, but clearly the large variation observed over the past 6 years could well be due to a stellar companion. Okay, a stellar companion. Yeah, so not a substellar companion. I see. Okay, this is not the whole story for this star. However, the trend of decreasing velocity shown in figure 2p is not smooth but shows significant bumps. To illustrate this, we have subtracted a second order fit to the relative velocities, and the resulting residuals are shown in figure 5. The second order fit was, okay, so this is the velocity, and here it's apparently dependent on the date, where BGD by Julian date minus 2.5 million. Okay, so this is the equation for the fit. These velocity residuals show a periodic variation with semi-amplitude of 25 meters per second and a period of about 2.7 years. Since the 18.4 meters second root mean square variation of these velocity residuals is larger than the external error for any other star, and since our observations cover a full 2 periods of this variation, we classify gamma sep as a probable low amplitude variable. Okay, so I'm not following along with what all the significance of what they're saying here, what is meant by a probable low amplitude variable, but I'm gonna keep on reading, and I'm gonna hope that maybe things make more sense as we get further into the paper. B, are the velocity variations due to companions? Yeah, okay. The low-level long-term velocity variations that we have found in 7 stars could, in principle, be due to something other than center of mass motion of the stars. However, it is unlikely that they are due to very long-period stellar oscillations, since a simple radial variation at 10 meters per square over 5 years would result in a doubling of the stellar radius. Okay, yeah. Similarly, star spots plus stellar rotation cannot produce the long-term trends, since spots would introduce velocity modulation on, I don't know what a star spot is, the time scale of stellar rotation period, which is less than 1.5 months for solar type stars. Okay, so yeah, they're talking about what these radial velocity variations could be due to. A serious possibility, however, is that variations in convective granulation patterns on the time scale of stellar activity cycles could introduce apparent velocity variations as suggested by Drabins. Granulation patterns cause the line profile asymmetries observed in solar type stars. And there's a long reference. Okay, observed in solar types. Okay, so granulation patterns cause the line profile asymmetries observed in solar type stars. It has been suggested that stellar activity cycles could modulate the granulation, perhaps through the influence of magnetic fields affecting either the granule velocities or filling factors or both. This could in turn cause variations of the line profiles on the timescale of the stellar activity cycle, leading to apparent velocity variations of perhaps a few times 10 meters per second. However, as suggested by Dravins, such variations would presumably show a correlation with chromospheric activity indicators. Wilson has shown that the classic indicator of activity CA pi H and K line reversals shows the effects of star spot cycles in solar-like stars. Fortunately, in our spectral region, there is a line of calcium, is that pi, or 2, that's 2, not pi, sorry, it's, okay. The infrared triplet line at 8662 Ångström, see figure 1. This line does not show an emission reversal, but the core still shows the effects of filling in by emission. In each of our spectra, we have measured a relative equivalent with arbitrary 0 point of the central one of the CA2 line. These values are given in column 6 of table 1 and are plotted versus time for each star in figure 2. The estimated uncertainty in the equivalent widths is typically 1 micro or 1 milli, Ångström. I think that's Ångström. The coefficient of correlation between the velocities and CA2 equivalent widths are, okay, the velocities R velocity and delta EW is shown in column 8 of table 3. Taken individually, one might conclude that there are some possibly real correlations present, for example 1 per and 46 UMAA. These are the stars. However, if there were a causal connection between the velocity and the CA2 variations, predominantly positive or negative correlation coefficients would be anticipated. This is not observed. The average correlation coefficient is positive 0.03. We note that an occasional apparent correlation or anti-correlation would be expected if there are velocity variations due to low mass companions on timescales similar to the cyclic variations in the CA2 line, which incidentally is the case for the Sun. We conclude therefore that activity cycles do not affect radial velocities at the 10 meters per second level. In the absence of any other plausible origin for the velocity variations, we propose that they represent center of mass motion due to companions. Okay, so I'm not sure of all the details in this text, but they are basically explaining other possible explanations for the data. That seems to indicate that there is a companion to this star, and they're ruling these possibilities out. C. Notes on individual stars. In the following discussions for the stars which are closed visual binaries, we have converted the astrometrically determined orbits to relative radial velocities using the prescription of Van den Bos. Parallaxes and V magnitudes have been taken from Bright Star Catalog, and where necessary, these have been used to derive masses for dwarfs using an assumed mass luminosity relation, the log of m over, well, okay, so the mass of the Earth, of the Sun, equals minus 0.06 MB. Okay, so this is how you calculate the mass. Not really sure. Okay, so this is a star, HR 509. No astrometric perturbation found by Lippincott and Ward from 37 years of data. CA2 lambda 8662 shows no evidence of variation. Similar to the HK data of Wilson, Campbell, and Walker, derived preliminary relative velocities for this star, which differ from the present results for the same data because of the more sophisticated reduction procedures currently employed. Okay. HR 937, no astrometric perturbation found by Lippincott from 63 years of data. We do not confirm the suspected velocity variability. We do not confirm the suspected velocity variability. Okay, I'm a reference to another paper. Okay. HR 1084, epsilon area, probable variable. Van de Kamp proposed that there is a 25-year period perturbation with 0.019 citation mark there, semi-major axis, but our relative velocities are not consistent with this orbit. Heinz 1978 believed the orbit is spurious since the nearby star Delta Aries shows a similar perturbation. The single spectral interferometric detection of a companion by Ballastet has not been confirmed in 15 subsequent observations by McAllister, nor by infrared speckle interferometry by McAfee 1987. Noyes 1984 found evidence of P-mode oscillations of about 10 minutes period. To minimize the effect of such oscillations on our velocities, our exposure time since 1984 have been a multiple of 10 minutes. IRAS data show a significant far infrared excess. Okay, HR 1325, no astrometric perturbation found by Heinz from 58 years of data. We do not confirm the suspected velocity variability. CA2 lambda 8662 shows clear evidence of cyclic behavior. Okay, I'm gonna look what the hell that means up. Okay, so it is calcium and it's a specific spectral line of calcium for the spectrographic measurements, although I don't know what they mean, what the evidence of cyclic behavior implies for the existence of a substellar companion. HR 2047, She1 Aurier, velocities predicted from the astrometric orbit of Lippincott and Worth, assuming B has negligible luminosity, are plotted along with our velocity data in figure 2e. The agreement is satisfactory considering the small astrometric amplitude. The eccentricity derived by Lippincott and Worth, 0.6, is obviously too large. A value around 0.35 is probably appropriate. We find no evidence for a late type secondary spectrum from two of our spectra near velocity maximum and minimum, each of signal to noise ratio about 1500, and conclude that the magnitude difference in the I band must be greater than 6.5 mag. This is nevertheless consistent with the speckle interferometric detection of Chi 1 Ori B at the 2.2 micrometer by McCarthy. A secondary mass of 0.17 mass of the Earth or the Sun, is the Earth, is implied. We have not tested for a third body perturbation in our velocity data. HR 4112 36 UMA, possible variable. Lippincott proposes there is a close unseen companion to A. However, from our orbit, assuming this companion has negligible luminosity Note the non-detection by McCarthy. We predicted an acceleration at 1984 of delta, so change of velocity 137 meters per second per year. Since the observed acceleration is only minus 4.7 meters per second per year, we conclude that the suggested astrometric companion is spurious. HR 4540 beta, possible variable status of astrometric perturbations is unknown. HR 4983, no astrometric perturbation found by Hans from 53 years of data. We do not confirm the suspected velocity variability. HR 1519, possible variable status of astrometric perturbations is unknown. HR 5544, from the astrometric orbit of Velen and the mass rate of Hershey, we predict that the acceleration of A due to B should be plus 12.3 plus or minus 0.8 meters per second at 1984. The observed acceleration is only 5 plus or minus 1.7 meters per second per year, which differs from the prediction at the 3.9 sigma level, where sigma includes the errors in both the predicted and observed accelerations. Uncertainties in the visual binary elements and mass ratio are too small to explain the discrepancy. We therefore classify the star as a possible variable due to a third body. Strand and Wobum and Duvent have suggested from astrometric observation that there is a third body in the system, but it cannot be a companion to A, since the proposed astrometric perturbations would apply a much larger velocity variation than we observe. HR 7462, no periodic astrometric perturbation found by Hans from 50 years of data. We do not confirm the suspected velocity variability. HR 7602, possible variable component B is a DM3F13 with unknown orbit. Several possible that the observed acceleration could be due to B alone. Component B. HR 7948, Hauptmann has given a provisional orbit for the gamma 1 minus gamma 2 Delphini system, period of 3,249 years. This yields an expected acceleration of 0.6 meter per square per year at 1984. We do not confirm the suspected velocity variability. HR 3957, no astrometric perturbation found by Heinz from 45 years of data. HR 8085, from the astrometric orbit of Jostis, we predict that the acceleration of A due to B should be 3.7 meters per square per year at 1984. The sign of this acceleration was determined from a single spectrum of 61 sig B obtained with hydrogen fluoride on 1986.4723, which gave a velocity difference between the components of 1,169 plus minus 118 meters per second. The relatively large error is the result of differences in the spectra of A and B. Using a parallax of 0.294, the predicted difference is 1,261 meters per square, which is in a satisfactory agreement. A low mass companion to either A or B was first suspected by Strand, while Deich identified low levels astrometric perturbations of 6 and 12-year periods. Our velocity data imply that if these perturbations are real, they must be in the B component. Heinz and Jostis doubt the reality of these perturbations, while McAllister and McCarthy saw no evidence of a companion to either A or B from speckle interferometry. Wilson's HK data for 61 sig A suggests a 7-year activity cycle. We would predict from Wilson's data a minimum around 1984, which is confirmed from our calcium 2 lambda 1862 equivalent width measures, figure 2.0. HR 18974, probable third body variations of 25 meters per second, amplitude 2.7 year period superposed on a large velocity gradient. Status of astrometric perturbations is unknown. Okay, so let's continue. We're finally at the discussion. So this is, I think, hopefully where the really interesting things is gonna be spoken about, but we'll see. So limits to companion masses. Okay, so there's a bit of maths going on. I think what we want to do is we're solving for the mass of the companion, so substellar companion, so the probable planets. For a companion mass of mass C and Jupiter masses M, I don't know what this is. Is that a 2? Is that a 4? I don't know. 2, 4. Let's call it that. In a circular orbit of period P in years and inclination I about a star of mass star, so solar masses, the derivatives of the radial velocity of the star will be delta V over delta T 2 pi, and this is the amplitude over the period, and then sinus times sinus of the 2 pi and time over the period plus some sort of phase shift, or let's just call it phi, and so the second derivative is 4 times pi squared times the amplitude over p squared cosinus 2 of the 2 pi t over the period plus phi, and here's the amplitude 28.4. I don't know where that came from, of the mass companion sinus I period to the power of a third times solar mass to the power of 2/3 meters per second. Combining these yields this, which is independent of the unknown phase phi, so we got rid of that. Upper limits to the derivatives can be attained from the slopes and the curvatures derived above. So the 1 sigma upper limits for these are simply delta V over delta T is less than the slope mass, so max equals the slope plus the sigma of the slope, and the second derivative is less than the curvature max. Anyways, solving for the companion mass, we have this. So this is how you would calculate the mass of the companion. This yields an upper limit line in the mass period plane, and an example of this for this star is shown in figure 6. Where do we have figure 6? This is companion mass diagram for tau Zeti. The radial velocity limits is from equation 4 and equation 6. Okay, so this is companion mass in terms of, what was that, Jupiter mass? While the astrometric line is from equation 7. Okay, this is the astrometry. This is how the, okay, so here we have the year. So as the period increases, the mass does. Not really sure. For periods less than 6 years, we have taken for an upper limit to the amplitude A is less than 1.414 sigma E. Okay, to derive the upper limit line from equation 4. What was equation 4? That's the amplitude. An additional constraint on companion masses come from astrometric observations. Again, assuming circular orbits, we have that mass of the companion is less than or equals to 1.5 times 1,000 alpha L pi p sun mass over the period to the power of 2/3, where pi p is the parallax and alpha L is the upper limit to the astrometric perturbations. It's difficult to determine an appropriate value for alpha L in all cases because of the range and quality and types of data available. However, to our knowledge, 13 of our 16 stars have been observed astrometrically, either to search for low amplitude perturbations or to determine visual binary orbits, and none show a convincing perturbation due to third bodies and visual binaries larger than a few hundredths of an arc second. We therefore take as a representative of 1 sigma upper limit alpha L equals to 0.01. Equation 7 yields the astrometric limit line in figure 6. The intersection of the two lines in the mass period plane gives a period independent upper limit to the companion mass given by this. This expression yields the upper limits to the companion masses shown in column 9 of table 3. The stellar masses were derived from equation 1 for dwarfs, for gamma squared del, and from the evolutionary tracks of Vandenberg for beta equal and sep and gamma sep. We stress that these upper limits are valid only for periods less than about 50 years, since this is the typical extent of astrometric data. The large range in these upper limits is primarily a result of the parallax dependence in equation 8. The median value of these upper limits is 8 what was it, Jupiter masses, or 9 of these masses. If we allow for the average value of sin 1/3 of I, we shall therefore say that 9 of these masses is the representative 1 sigma upper limit to companion masses for a period of less than 50 years. For the possible or probable variables, we have derived lower limits to the companion masses by taking half the observed velocity variation as a lower limit to the amplitude in 12 years, twice the interval of our observations as the lower limit to the period. These are given in column 9 of table 3 and range from 0.9 to 1.6 of what was it, Jupiter masses? What was this mass? Yeah, yes. For gamma sep, the third body in the system has a companion mass in I approximate to 1.7 Jupiter masses. Since we have identified a period to the radial velocity variations, the lack of information on astrometric perturbations is not a concern in this case. This star therefore has the firmest evidence for a very low mass companion. In summary, we find that of the 15 stars examined, She1 Ori A is not considered here. None show evidence of a moderately close, a period with less than 50 years companion, or mass greater than roughly 10 Jupiter masses. 7 stars do show evidence of companions in the 1 to 9 Jupiter mass range, assuming that these companions have orbital periods less than 50 years, which is certainly true for gamma sep. Okay. B. The companion objects, are they brown dwarfs or planets? Okay. It's clear that none of our program stars has a close substellar mass companion in the brown dwarf range of 10 to 80 Jupiter masses. This is consistent with many other recent surveys with brown dwarfs, which have so far failed to turn up a single confirmed candidate. The report by McCarthy, Probst, and Lowe of a brown dwarf companion to Van Briesbroek 8 was apparently erroneous. infrared searches for faint companions to red and white dwarfs in the field and open clusters by probes. And O'Connell, Jameson, Sherrington, and Giles, Zuckerman, and Beckman and Kumar have turned up no substellar companions to brightness limits corresponding to about 30 to 40 Jupiter masses. Searches for isolated brown dwarfs by Bosar and Tyson, Chester, and Bosar, Tyson, and Tyson have failed to identify any candidates. It can be argued that the mass limits set by the foregoing surveys depend on poorly understood cooling curves for brown dwarfs. Okay. This cannot be said for the survey of Marcy et al., in which they saw dynamical evidence of low mass companions. They monitored 65 M dwarfs for low amplitude velocity variations and found non-existent with a brown dwarf down to a limit of about 10 Jupiter masses. Now, Marcy now believes that, so a reference to another paper, now believes that the companion to Gliese 623 is stellar. Okay. All of this evidence suggests that brown dwarfs are rare or perhaps non-existent, at least as companions to normal stars and possibly also in the field. If conventional brown dwarfs, 10 to 80 Jupiter masses, are so rare, at least as companions to normal stars, how are we to classify the companion objects that we have found? For 7 of 15 stars, there is a possible or probable companion in the range 1 to 9 Jupiter masses, assuming periods less than 50 years. Such a preponderance of very low mass companions combined with the absence of conventional brown dwarfs implies that there is a gap in the distribution of substellar mass objects. This suggests that the 7 companions we have tentatively detected might be more closely related to planets than to brown dwarfs, and that these objects could represent the tip of the planetary mass spectrum. Additional information is required before a firm conclusion on the nature of these companions can be reached. Alright, so this felt like a very rigorous breakdown as to why these variations in the radial velocities of these stars that they've looked at might be due to planets. Apparently, it could also be brown dwarfs. I don't know why that is. Do brown dwarfs not give off as much light, but they are heavy? Is that the idea? I don't know. But regardless, they're here arguing that, the data suggests that this could be planets. And most of these planets would have a period of less than 50 years and a mass of, I don't know. Masses in the range of 1 to 9 Jupiter masses. So that's pretty cool. We're indebted to the staff of CFHT for their invaluable assistance with the hydrogen fluoride cell observations, and to the time allocation committee of the CFHT for their strong support. We are grateful for their assistance. Okay, so here they are. Thank you. They're sending their thanks to people. All right, so we got through the paper. I didn't even have a look at most of these figures. I think I might have taken a dive into the deep end with this paper. It was still interesting, but definitely there was a lot of things I simply did not have the appropriate prerequisite knowledge. So that made it a bit hard to understand. However, I still found it was interesting, and you have to start somewhere. So, okay, so a short mention regarding this part. I felt when I read it, I didn't really understand it. A serious possibility, however, is that variations in convective granulation patterns on the time scale of stellar activity cycles could introduce apparent velocity variations as suggested by Drabins. So the way that I understand this is that it could be the case that these stars have these cycles just as our sun has this 11-year cycle that would have the same effect on the spectrographic measurements that a companion tugging on the star would have, or you could misinterpret the data in that way. However, if that was the case, then there would be other things that you could see in the spectrographic measurements, which here they have not found. So that's why they conclude that activity cycles do not affect radial velocities in the 10 meter per second level. So it would apparently have a bigger effect. In the absence of any other possible origin for the velocity variations, we propose that they represent center of mass motion due to companions. Okay, moving on. So in this part, it seems like they are it's clear that it's something tugging on this star, so there's something influencing the radial velocity. The question is, what is doing this? Could it be brown dwarfs or is it planets? Because the only option is not planets. My gut feeling would have been, okay, well then it's, if something is tugging on it, it's probably a planet or asteroid or so. But for here, it seems to be stand between either planets or brown dwarfs. And they then go on to say that it's clear that none of these substellar mass companions has the mass that brown dwarfs have. And additionally, this is aligned with other findings that brown dwarfs are either non-existent or exceptionally rare. So, okay, when they say this, it's clear that they don't have that mass. I'm guessing they're doing that by here solving this equation for the upper limit of the mass of the companion. What I don't understand about this equation is the mass of the stellar object, so the star. I don't know how we get the mass of the star, but maybe that's obvious for people reading these kind of papers, or maybe that it's something I missed, but I will leave that for now. Okay, going back to the abstract, I feel as if, this pretty much summarizes the way that I've understood this paper. Basically, they have measurements of a bunch of different stars, and they're looking at the radial velocity of these stars via the Doppler effect. And when they're looking at these, they can see variations in these radial velocities, and the question is, of course, then what's causing these variations? And for two of these stars, it shows very large radial velocities variations, so a few thousand meters per second, and that's probably due to stellar companions. Okay, so now I don't know what they mean here then, if this is can this be a brown dwarf, a planet, or no, it's a stellar companion. Oh, it's a star. Okay. Additionally, for 7 other stars, it can be seen that they have a small but statistically significant trends in relative velocities. So, and they can conclude that this is not due to brown dwarfs, but rather it's companions of 1 to 9 Jupiter masses. So for 7 of these stars, they believe that it might be planets. So that's pretty cool. That's this paper. That's the start of the series. Yeah, it was a lot to learn. I have a lot to learn, but yeah. Okay, last thing regarding the binary. That's seems to be just the way that they talk about this. Yeah, so if the star is actually not a star but 2. So here, for example, when they're talking about Xi or Ea, the star Xi or Ea is varying under the influence of a stellar companion. If it was a planet or a brown dwarf, they would have said substellar companion, and it's discussed further below. The star Gamma Sap was not previously suspected as a binary star system, but clearly the large variation observed over the past 6 years could well be due to a stellar companion. Okay, so